Good afternoon, everyone. Thank you so much for joining us today. My name is Steph Nelson. I am an application engineer for Siemens, and I will be your host for this webinar. Your presenter is Pete Schaldenbrand. Pete, would you like to introduce yourself?
Hi, I'm Pete Schaldenbrand. I'm also an application engineer at Siemens along with Steph, and I'd be very happy to talk to you about step-by-step going through the software to perform transfer path analysis today.
Yeah, Pete's webinars I feel like are always pretty fun, so I'm excited to see this one. All right, Pete, you ready to teach us about how to do transfer path analysis?
Yep. I'm going to step back and talk first a little bit about what transfer path analysis is and what kind of data we need before we go through step by step in the software building a TPA model. In general, transfer path analysis is a technique to try and figure out in a structure where some unwanted vibration or noise is coming from. Like in this particular case, you can imagine this operator ear here maybe. There's some sound getting there, and we'd like to figure out, is it this gearbox or is it the electric motor that some vibration is coming through that's then exciting the structure that then causes noise at the operator ear, for example. It's a complex structure with airborne and structure-borne components, and we're just trying to potentially figure out what components here inside this piece of machinery are causing that noise. To do that, we break the problem down into a few components. Here I have a receiver, and we'll use a car example for most of the stuff in this webinar. The car example that we can all imagine, if you're driving along, you can hear noise at your ear that comes from a variety of sources. So for example, you might hear your motor, whether it's a combustion engine or an electric motor. You can hear that. It might sound very loud. And the question would be, how is that getting to your ear from the electric motor or the combustion engine? One way it can get there is what we call airborne. And this would be the surface of this motor is vibrating, and it acts like a loudspeaker, and it creates pressure pulsations in the air that radiate off of the source and get to our ear. And it could go through like a hole in the dash, for example, or straight through the dash. That's called airborne because from the source that we are considering, trying to figure out how sound is being generated at the operator ear, this airborne noise is starting from the source in the air, from that purple object. Structure-borne would mean that there's some physical attachments here, and again, the source could be vibrating. That causes some vibration in the structure, and then sound radiates from the structure over to the operator ear. This is called structure-borne because it starts from the source into the structure. And even though it goes airborne eventually, it doesn't start life from the source in the air. It starts life from the source in the structure. So it's structure-borne, even though at some point it goes through the air. Hopefully that makes sense. Do you think I'm confusing people, Steph, at this point, or is that?
No, I think it makes sense to me. Hopefully, no questions yet.
Okay. We would look at this source, this purple box, and we'd want to know, is the sound getting to us starting from the air around the source or starting from the structure around the source? For this webinar, I'm really going to talk a lot about this structure-borne noise. These are some terms that you'll see on the slides that are coming up. P would be a sound pressure measurement, so we'll just call it a P. Force is F, uppercase F. A is acceleration. FO is an operational force. So when the source is running, the motor or combustion engine, this is the forces that it produces. Sometimes we might quantify a transfer function, like a pressure over force transfer function, by hitting the structure with an impact hammer. That force won't have that sub-O. That's going to be, for example, a P over F, where you artificially excite the structure to get this transfer function. And then we got some other terms here. Breaking this down a little bit, here, and I think this is very helpful in general when you're trying to do a transfer path analysis. If you can imagine a mental cut, if you will, that separates the source from the structure, like that dashed yellow line. Anything that crosses that dashed yellow line between the source and the structure is considered a path. Any path, we're going to take measurements on one side of that dotted yellow box and on the other side. On the inside of this yellow box, coming out of it, there's these physical attachments. So these are paths that attach the source to the structure. We'd like to know the forces that come out mechanically into the structure in order to do the transfer path analysis. And in this particular case, you can see there's a sub O there because we're interested in the operational forces, right? Could be that the force at mount location 1 is bigger than the force at mount location 2 or vice versa. But knowing what those forces are is very helpful for doing a transfer path analysis. And then to get over to the operator ear here, Steph, how do we know how much operational force results in how much sound pressure over here? What measurement is that?
Frequency response function?
Yeah, we would need a frequency response function, that P over F. And notice there's no sub O here because we quantify that ratio by doing something like an impact measurement or a shaker measurement or something like that. You can also do analytical work like CA work to come up with the transfer functions. You could use a combination, real operational forces, analytical FRFs, or vice versa if you wanted to. But yeah, we really need, at the end of the day, 2 pieces of information for each path that we're considering. We need to know the force coming out of the source, and we need to know the transfer function from the source to the target location of interest. And it doesn't have to always be an operator ear. It could be the vibration at the steering wheel, vibration on the seat, could be the back seat, etc. And we do something very exciting with these functions. We have the force versus frequency, we have the transfer function versus frequency, and to know how much sound is coming through path 1, sound that's being registered at the operator ear, what's the math operation that we do, Steph?
Oh, a simple multiplication.
Yeah, you take that force, multiplied times this P over F, the forces drop out, right? This is an operational force, not this artificial force. And then you would get the amount of sound that's coming through the path. So we take our green functions, multiply it times our orange function here, for example, and then we would get P1 and we would get P2. This is the sound coming from that first path, right? This is the sound coming from the second path, and then we get the total sound. And we would care if P1 is bigger than P2 or vice versa. That would give us some clue as to which path we need to address to eliminate or go after the problem. That make sense so far?
Yep.
Yeah. You and I do a lot of testing for a living there, Steph. Why don't we just measure this P1 directly? Why do we have to measure an FRF and a force?
Yeah, why don't we just measure the P1 directly? It'd be so much easier.
It would be. I guess to measure P1 directly, we would have to eliminate P2, right? So back here, that would mean turning off this path, maybe disconnecting the mount or something. If you had 4 mounts that attached your engine to your car, could you easily drive around with the 3 mounts not attached, Steph?
No, I would say that'd be tricky.
Yeah, so from an experimental point of view, it would be very, very tricky to measure directly these. So it's not possible to measure these directly during operating conditions unless you really disturb the structure, and then your engine would probably fall out or something like that. And it's also helpful to have the FRF and the force, because this will tell us if it's the motor or the combustion engine that's really high, or if the structure is very sensitive, so we'd have even more insight. First, we'd know which path is the biggest, and then we might look at these things to figure out what to do. Like, do we need to address a resonance or something else? In fact, let's say the sensitivity of this path is very, very high. Does that mean that P1 is going to be a problem? You know, if I draw here, I'll make up a number, 10,000 pascals per Newton, the highest sensitivity we've ever seen in a peak on a structure. Is for sure P1 a problem path?
It could be, depending on other factors.
Like the operating force?
Yeah.
Yeah, if the operating force was 0, this thing could be as high as it wants to be, right? Nothing's going to come out of path 1. It's important when you're doing TPA to, again, consider the structure and the source, both of them, and not just get hung up on one or the other. Otherwise, we might get misled, right? Because it's the combination of the force times the transfer function that matters. On the other hand, if we have really high operating forces, would P1 be a problem? The answer would be no,
Definitely.
because the sensitivity of the structure could be 0. It's the same story. We have to really look at both and then see the total, etc. Okay. All right. So with that great background, I'm going to go through the steps of creating a transfer path model. If you're using TPA software in Simcenter Testlab, there is a transfer path analysis add-in, 98 tokens. You turn that on, and you'll get these 3 steps over here. And what the transfer path software does is it doesn't acquire data. You have to have data that's already been acquired. So for example, in this section of my project, I have some forces. If I grab these and drop them in the display, you can see they're forces of 4th order versus RPM. Does that make sense so far?
Yep.
And then I also have some FRFs here. I can drop those in the display. So I got to have already measured FRFs and already measured forces in order to do a transfer path analysis. Let me maybe make a 1x2 display. So here's my FRF. It's pascals over Newton, and it has this label here. I don't know if you can see that easily, Steph. I can make it a little bit bigger. If you're looking at that label, I know you know nothing about the structure that I'm working on, but what would you guess about this transfer function? Why?
It's in the X direction.
Yeah, although the forces, but how about the response here?
Oh, it's a pressure response?
Yeah, which is directionless. If I look at these channels over here, the top 2 are probably pressures, these are forces, and this node 7 with 3 zeros, 2, 5 is probably an operator ear location. Does that make sense?
Sure, yeah.
Yeah, and you would know that when you prepared or acquired the data. In this case, do you think this data was acquired or is it from a different source? Whenever you see a bunch of digits like that, does a thought come to mind? Like, do test engineers always use a bunch of digits?
No, you think it might be simulated data?
I think it's simulated. It's data from simulation. And again, you can bring data in from simulation, no problem with Testlab. So it's not like you have to use test data. Okay. Here, I also have this order, 4th order, right? And it has this node, 1 million in the X. Simulation data could easily get up to 1 million nodes or more. Do you think it's significant that the transfer function here also has 1 million in the X in the denominator?
Yeah, I would think.
Yeah, because the transfer path software will actually look at these names to know which force to multiply the FRF by. If you're going to use the Testlab transfer path analysis software, you really have to take care of the names so that the names of the forces match the denominator of the FRF. Here I can see that there's forces at 1 million in the Y and Z, 1,000,001, 1,000,002, 1,000,003, X, Y, and Z. If I look at the FRFs, it's the same thing. There's 1 million X, Y, and Z, 1,000,001 X, Y, and Z, et cetera, et cetera.
Yep, the force names have to match.
Yep. Force names have to match the denominator of the FRF.
All right.
It'll make your life a lot easier. Now, what if they don't match? Is that possible, Steph?
It is. You can rename them though.
Yeah, you can right click and there is a rename, but there's even something better, which I think a lot of people don't necessarily know about. If I right click here on this project, there's actually a alias map. Ever heard of an alias map?
I have.
Yeah,
Useful if you
here.
misname your geometry.
Yeah, right. If you have a geometry and you've took measurements that have a different name than the geometry, you can create a list of the geometry points and then the names of the measurements and match it up. But it can also be used for TPA. Instead of going through and renaming like 10,000 FRFs, if you just type in the name of the FRF as you acquired it and the name you want it to be, This will take care of everything. You don't have to do a bunch of manual renaming. You can just kind of name them all at once with the alias table. At the end of the day, it's going to figure out which forces go with which FRFs based on the names. Okay. If I take these FRFs, put them in the input basket, I got my forces. I'm going to add those to the input basket, and then I'm going to go over here to TPA model. And here I tell it what the paths are and what the target locations are and a bunch of other stuff, and I'll step through this. So I'll hit read input basket here, and again, we have two of these with an S in it. And over here, you can see there's some double arrows. There's something called targets, paths, indicators. What would you guess these two need to go in? They're the
Well, they're not
sound.
paths. Maybe they're targets?
Yeah, they would be targets. These are where we want to calculate the path goes to. And you can have more than one target. We showed an operator ear before, but you could have the operator ear. Maybe that's what this one is. And then you could have the passenger ear, because maybe a car company cares about the passengers, or even the rear seat passengers. You know, there's no limit on the number of targets. You just have to measure the FRFs from the force inputs to those target locations. These, what would you guess? These are
The indicators?
or you could guess paths, because these are the paths that's going through. We'll get to indicators in a second. And the word indicators is a little confusing. Basically, if you have the forces directly, you can put them in the paths. Indicators, I think it's another word for indirect. If you don't have the forces directly, if you measure an acceleration, and then you're going to use that to calculate the force, so you'll indirectly calculate the force from the measurement, you put it in the indicators. So if I had accelerations, I would be using indicators for the indirect calculation of the forces. But in this case, again, I'll go back to the navigator. When we looked, we had newtons of force for all these fourth orders, and then we had the transfer functions from force to pressure. And so we just have to multiply them. These are really the only things I had to define. Later, we're going to go through the mount and matrix method, and then we'll use the indicator section. Here, I can read the operational condition. We got fourth order. It goes over a certain RPM range. And so I've set up for a direct TPA where I have forces. And this is pretty common with simulation. You can calculate the forces directly in your simulation. So I have those, and then I have the FRFs. The next step in this model definition is to go here to the FRF selection, read the input basket again, and I can verify that I have the FRFs from my target locations to my paths, and I can see them all. So there's 12 FRFs here, 12 FRFs there. How many physical attachments are there here, Steph, between my source and my structure?
4?
Yeah, there's 12 total. Each location, you know, unlike the PowerPoint I was showing earlier, we had one force in the vertical direction. Here we got forces in all three directions, X, Y, and Z. So that's one attachment, a second attachment, third attachment, fourth attachment. I don't know where these physically are on this model, but the person who took the data hopefully did and would have told me so that I can locate the right mount when I'm done here or the problem. Operational data, I can also read the input basket, and then I can, again, see all those forces. That make sense so far?
Yep.
Yeah, so in this TPA model step, I'm basically defining what paths I want to evaluate, what operating conditions, call those cases, and then I'm telling it which data I want to use. If I clear this out, you know, when it's red, it means there's no corresponding data. When you read the input basket, fills in green. If some of these don't fill in green, you're missing some data that you defined in your model. So you hope it all turns green, and then you want to look at it and make sure it's the data that you wanted. Same thing over here, okay? So I got all my data defined, and in my next step, I'm going to do another math operation there, Steph. What do you do with the FRFs and the forces mathematically?
You multiply them?
Multiply them. The TPA load step, and here there's different methods for calculating the forces, but if you know the forces directly, all we're going to do here in TPA is do a multiplication. These are the things that are available. I hit apply to load table, and it's doing that multiplication for me. With the other methods, mount method and some of the other ones, it gets a little more exciting, but when you have directly known forces, you can just do this directly, multiply them, and then go to TPA results. Normally you come into this contribution display, you would update the display. There's a few ways of viewing this, but this one I think is interesting. So I got fourth order selected. I got my RPM down here, which goes from 920 RPM to 4,500 RPM. It's got the calculated total of all the paths here, and then it has the individual contributions of each path along the side here. 1,000,001 in the Z, 1,000,002 in the Z, 1,000,003 in the Z, etc. Would you say that one of these paths is maybe more interesting than the others? What do you think, Steph?
Probably the first 1,000,001 in the Z.
Yeah, 1,000,001 in the Z has a red higher level at, you can see what RPM that is, right at 3,744 RPM. We got a high level there in 1,000,001 in the Z, contributing to the total. There's even high contribution from it at 1,277 RPM. Would you say that 1,000,001 is the only path contributing to those two problem RPMs?
Nope. 1,000,002 in the Z looks like it's pretty high as well.
Yeah. Yep. And even in 1,000,003 in the Z, at least for this one, it's pretty big, huh? Which directions are the least contributing?
The X directions would be my guess.
Yeah, these X's, they seem pretty mellow. They're not contributing too much. They're even a cool shade of blue. It looks like our vertical direction on our physical attachments, whatever orientation we measure that in, are the main contributors. And that's kind of what we're looking to do with transfer path analysis. We're looking to understand which paths are the biggest contributors. Up here, there's a path-specific display. Click on that, and you can say multiple paths here. And this lets you look at different paths. 1,000,000X, was that a big contributor?
No.
No, and the green looks significantly lower than the red. The red is the total of all paths, and those things that looked red in that color map, that 1,200 RPM, and you can see that big peak there, 1,290, I should say, and then 3,700 RPM. They're pretty big. If I was to go to, what was it, 1,000,001 in the Z, that looks like a pretty big contributor, doesn't it?
Yep, I would say.
Yeah, you can see that here in the calculation of these, and you can see them all individually, see how they compare to the total. If I highlight them all, it sums them all together. There's actually two curves here, but they're identical because they're on top of each other. And
so one of the sum two together.
I could sum two together. If I highlighted two, so I'm holding down the control key, that's the sum of those two, sum of those three. I'm going to sum them all, and then I'm going to do the opposite. You ready for this, Steph? We said 1,000,001 in the Z was a big contributor. If I hold down control and I click on this, I have removed 1,000,000 Z from the total. I'm doing that virtual disconnect without the danger of my engine falling out. Did I solve the noise problem here?
No.
No, because the green curve has same peaks or similar peaks to the red curve?
Yeah.
Yeah, and by the way, it could be that paths were canceling each other. The TPA takes into account phase. So what were some of the other big contributor paths?
1,000,002 in the Z, I think.
Yeah,
was the next one.
I'll take that out. Now how are we doing?
A little better.
Yeah, at least on this one, seems to have removed the peak. But this one, it's still there. What was the other contributor?
1,000,003 in the Z.
Yeah, let's try. Oh, it looks like might be gone. So if I put that, in fact, in this case, if I put any one of these three back in, and I'm holding down the control key, you have that problem. What this is telling me is something very useful. It's telling me that I need to remove all three of these in order to get rid of the problem. Removing just one of the three or two of the three isn't enough, which is what this indicated, right? There's three red things here. They're all about equal magnitude. When it comes to troubleshooting, it can be very hard. You might think there's one mount that's a problem and spend a lot of time on it, but this is telling you got to spend time on all three mounts or you won't get rid of the problem.
Yeah, and the top graph is just showing you the averaged SPL for the order.
Yeah, so it's just showing the averaged SPL. Later, I think we'll have multiple orders. You can just use this to select which order you want to look at. I wouldn't read too much into the amplitude there. All right, so we got this just to show something practical in the software. There is this grouping over here, and you can do things like you could grab Z directions. You could call that vertical, for example, create a group of vertical, grab X directions, call that fore aft or something like that. And then the Y directions could be lateral, for example. And then here you can update the display and you can see things, the verticals versus the laterals, as opposed to the individual paths.
Yeah, that looks handy.
Yeah, it can be handy, like if you have engine versus exhaust versus intake, however you want to group it up, you can do that, or left mount versus right mount, etc. Hopefully that helps people understand a little bit about the software. And it's a three-step process. You define the model, you do the force calculation, and then you look at the results. And by the way, back here, this at the top is what we're analyzing. So when we first came in, if I clear that out, there's no definition of what we're going to multiply together, force-wise, etc. This is what's available. And when we hit this apply to load table, it updates this matrix. And notice in this case, I could apply to load table one path at a time. And I could actually do a combination of different methods, mount stiffness, etc., all in the same model. But this is the active model. In this case, it just made sense to do it all at once. I'll try to touch on that again later, and hopefully it'll make even more sense. Okay, that whole indicator thing. Sometimes it might be hard in practice to measure forces directly. You know, it's easy for the simulation data that we had for them to create the forces. One way would be to try and use a triaxial load cell, but you'd probably interfere with the dynamics of the mount and it can be kind of big. So instead of doing a direct measurement of the forces, some people will use a method called the mount stiffness method. And in the mount stiffness method, we're going to take advantage of, I guess it's probably one of Newton's or Hooke's laws, that F equals Kx. And you can see here we have two X's. Sub A here is the displacement on the active side of the mount. The P here is the displacement on the passive side of the mount. So the passive side is attached to the structure. The active side is on the motor or engine. That's vibrating a lot. You take the difference in displacement, multiply it times the mount stiffness, and you get the force. This mount stiffness, by the way, is not usually a single number. They're curves that the stiffness, newtons per meter, or something like that, that are a function of frequency. So you need the mount stiffness for the mount and potentially in all three directions. If you're doing all three, you need the active and passive side. We typically measure acceleration, double integrate to displacement, subtract it to come up with the force. And again, the mount stiffness can have phase, as we saw earlier. And typically when they go to test it, you got to be careful to maybe have the right preload. If you have a piece of rubber that's acting like a mount, if there's 300 pounds resting on it, it might have a different spring rate than if there's nothing resting on it. If you have 10 millimeters of displacement versus 1 millimeter of displacement, the mount could act differently. So there's test rigs that'll go out and measure the mount stiffness, or if you have a good mount supplier, they might have those curves and they adjust for those things and can give you the stiffness. In addition to the stiffness, we're going to measure now acceleration on the active and passive side of the structure. So instead of just having a force here, we got double the amount of information because we have to have stuff on the active and passive side. We still have our FRFs, and then with the mount stiffness and with the displacement on the active and passive side, we take the operating displacements, subtract them, times the stiffness, times the FRF. This term will simplify to just the operational force, which we have there, and then we can go. So these were the equations that we had before. Now, instead of having the force directly, we're measuring it indirectly. We'll be using indicators in the software. This is the basic form, okay? Again, this term simplifies to the operational force, and then we still multiply by the FRF. Make sense as far as what we want to do there, Steph?
Yeah, you have to measure in more locations though, right?
When you say more locations,
You have to measure an active and a passive side on your
yeah, we have to
mounts.
do the active and the passive side. So same FRFs as before from the passive side of the mount on the structure to the receiver location or target location, right? But yeah, here, instead of a single force, we're going to measure acceleration, active and passive side. Is that what you meant?
Yes. Yep.
Yeah. It's not too much more information, right?
No, just a little bit more,
Yeah.
but it's easier.
Back here, I got a different set of data, which has, for example, has mounts. If I look at the mount here, you see it's Newton per meter. A lot of times people look at this in Newton per millimeter. Depends how you like looking at your mount stiffness. And you can see it's a curve versus frequency. And I have different mounts in the structure. They're at different spring rates as a function of frequency. Then I also have things like the FRFs. These would be from, if I look here I have a microphone location. This is probably the target. Again, it could be an acceleration like on the seat or something, or in that microphone location, somebody who measured it would know where mic 1111 is located. It could be the driver ear, passenger ear, whatever. So I got FRFs. And then I have operational data as well, which is under this folder. And I'll open that up. And if we look at this operational data, notice I got a body 3 here, but then I also have a engine 3, right? Why would I have 2 accelerations?
Is one on the active and one on the passive side?
Yeah, and which one do you think's active and which one do you think is passive?
Passive is body, active is engine.
Yep, because the engine is doing a lot of moving, right? I guess we have visual confirmation that it's the active component because its vibration levels are a lot higher than the passive side. When we pass through this rubber mount, the high levels of vibration on the engine are reduced and you get a lot less vibration on the structure side. And notice there's, again, the naming is important, body 3, engine 3. If I go back to my mount data here, these were the X directions. There is a mount here, body 3 to engine 3, and this is the mount that connects them. And you know how I know it's what connects them?
Because it's the same names.
Yeah, it's, again, key if you're using this software, you better have the same names. If you don't have the same names, then what would you do again? Remember?
You could rename them if it's a few, or you could use the alias table.
Yeah, you could rename them or come up here, alias table, and match them up that way. And these names, by the way, have to be exact. Body that starts with an uppercase B versus body that starts with a lowercase b, the software treats those as different. So it has to be the exact same name, including the case. And you have to have directions. In this case, I do have all the data, and we'll go through under our TPA model and create it. I I forgot to put things in the input basket here. So I need my operating data. Got a bunch of orders here. So I'll put those in the input basket. I got a whole slew of FRFs here. And then I got my engine mounts. And I'll read the input basket. And what this is really doing is just reading the IDs from the data. You would have want to have done the alias thing before this. In this particular case, we would pick the microphone, because again, we would know in advance that this was the measurement location of interest. That's our target location. And then we would pick our paths next. And in this case, it's these, and we know this in advance, that it was the body locations. There's a XYZ here, 1, 3, 4, 7, 8. The fact that we have 15 rows with XYZ, it means that there's 5 attachment locations. We have 5 attachment locations between our structure and our source. Indicators. What do we need there, Steph?
The other body mounts that would be measured on the passive sides, 11 through 23.
Well, bodies, all the bodies are on the passive side, and these are our paths. What we actually need at each, I go back here, for each mount, we need the passive side of the path, right? But we also need the active side of the path. Yeah, so like if I go back here, I think this is kind of the key. This we never had before. This is the active side, right? That's on the motor or the engine. We need those, and then we need the corresponding locations as well. Here we have the passive side, and then we have the corresponding active side, because we're going to have accelerations. Notice the unit here is accelerations, and we're going to use these accelerations to calculate these forces. We do not actually have any force measurements in this case.
So we measured a bunch of passive sides that we didn't measure the active sides on. Is that what the other ones are?
Yeah, we did. That was just to fool you, to make the questions a lot harder. Again, if we're doing mount method, we need passive sides accelerations and we need active side accelerations, and they should correspond. And actually the software is nice. If you've picked the paths, which are based on the passive side, notice, I don't know if you noticed, I'm gonna maybe just clear these back out. Over here, there's this mount table forming. And so when we pick the engines, it's, well, there's none of these are paths. These must be maybe active side vibrations. So it automatically put it there for us. Did you see that?
Yeah, that's nice.
Yeah, and then here on the body, if I choose those, because I need both the active and passive side as indicators, it's, well, those have the same name as the paths. These must be the passive side vibrations. So it lined that up nicely for us. Isn't that cool?
Yeah.
Yeah. Here you got what type of operational forces. If I read the input basket, notice this time I have multiple orders that I could analyze. There was half order, 1.5 order, third order data there. And then here you can have some fun. You can say, okay, I got a body side location for my passive data, and then I need to assign it one of these active sides. In fact, the names don't match because one's body, one's engine, so you're matching them up for the software here manually. Now, if I'm smart with my naming, I might have them all in the same order, so to speak, and I can match them up, right? Let's see if I did a good job. 3Z to 3Z, 4X to 4X, 4Y to 4Y. 7, 7. So looks like I got them well matched, active to passive side. This mount table here, we're adding this to the model. We're doing a little bit more here than we did before when we had directly known forces. So then I'll go to FRF selection here. I'll read from the input basket. And yeah, there could be some data that isn't there, but we have all our path FRFs. Looks like one FRF sticks out here, maybe the body 1Z. And then we have our operational data. Actually, in this case, I do have some directly measured forces, but I got all sorts of accelerations, active and passive side. And now when I go to TPA loads, which of these methods will I pick in order to do my force calculations?
We're doing mount stiffness.
We got the active and the passive sides. And it's telling me I haven't defined my mount stiffness yet. I actually have to go in here and I can go into the mounts directory and I can grab the mount data. And it's actually, in this case, a kind of a manual process. I want to connect 1Z to 1Z. I can grab the 1Z to 1Z mount, again, based on the names, and then connect it all up. Usually there's not a ton, so this isn't a huge deal. Okay. So just bear with me for a second. Part of this, I wanted people to be able to see exactly what they have to do in order to create these models. Seven Z, 8X.
Nearly there.
And then, yeah, and then after you've done this, don't hit the clear data. This is all the mount stuff ready to go. I can say apply to load table. Actually, just select, and then I'll put them all up there. Notice, and just to point out, if I had this and I say apply to load table, I'd get two methods like that. I did have some directly measured forces. So I have these defined in a stiffness way. These were directly measured. I could say apply to load table, and I could have a combination of directly measured forces and stiffness as well, method or mount method. But in this case, we'll just go all mounts, okay? And then I can look at my results here, update the display. Now this bar at the top actually lets you pick things like third order. And would you say there's one path that contributes the most here?
For sure, body 1Z.
Yep, so body 1Z. And again, if we go to this path specific, we can start looking for third order. It's bringing up all the data for the path. We got the calculated and measured total of all the paths. So it looks like there's not a path missing. Body 1X is in blue here. And body 1X is the amount of sound at the operator ear or the microphone location due to path 1. And that's a combination of the force times the FRF. And then it also shows us the mount stiffness that was used and the active and passive side accelerations. And normally if your mount's doing a good job, the passive side should be less. So we could look at body 1Y. You can see there's a big difference there. We can look at body 1Z, and body 1Z was the big contributor compared to body 1X. Actually, maybe I'll go back to body 1Z here and I'll make the limits fixed just to make this a little more dramatic. If I go back to body 1X, what would you say one of the big differences is between body 1X and body 1Z, and why body 1?
Contribution.
Yeah, it's a lot higher, right? So in this case, 1X is not contributing very much, but body 1Z is. And would you say it's the FRF, the structure, or the force, the motor or whatever, that's creating the problem?
Possibly the force, it looks like. The peak is up in the force.
The peak's up in the force, but I think it's a perfect storm. We also have a peak in the FRF, the force, and the structure are combining to cause the problem. If you're at a company, you get to blame both the structures people and the source side people.
Someone asked a quick question. They said if they are measuring acceleration on the receiver structure, are they indicators or targets?
If it's vibration on the receiver structure and you like seat track vibration and you care about paths that are causing the seat track vibration, those would be targets. In the examples we've been using, we've had sound as a target. It's not always sound that's a target. Sometimes it's vibration as well. I'm going to add on something else here, TPA component editing, because I think this is interesting. You'll see these things that are grayed out here that say editing. I can say open edit, and then I can come to this peak here, and I can say, hey, I want to remove that peak and reduce it by 90%, and it'll actually recalculate for me the new sound level. So I could get an idea if I could reduce the sensitivity of the structure by this amount, how much the sound would be offset, which is kind of nice. And you can do the same thing for the vibration and everything else. I'm going to cover the matrix method. Sometimes, if we don't have a soft mount, we have a stiff bushing, like a suspension component or something like that, or a metal-to-metal contact, no rubber isolator, the vibration on the active and passive side would be very similar. In this case, you can see these look pretty similar, active versus passive side. And if we measured this and we got a difference of just 0.1, we'd say that's very little measurement error. If I was to use the 0.1 versus 0.0 here and subtract the difference, the force estimate would be different by a factor of 2. So with stiff connections, the mount assumption doesn't work because the passive and active side are nearly the same vibration level. So we have to use a different method. And what we'll use is a local FRF, acceleration over force, measured at the passive side. I could measure this at the same time I'm measuring the FRFs to the target location, but in this case, I need this local FRF as well. And I'll use that local FRF with passive side operational acceleration. And I'll take that operational acceleration, the local A over F, acceleration over force, invert it. After I invert this, it's F over A, and these accelerations will multiply to give me my operational force. There's another way to get the forces. You're using an FRF, a local FRF that you invert in order to do this. The only problem with this technique is an FRF could be close to 0 at an anti-resonance of a structure. If you invert something that's close to 0, what does happen there, Steph?
You get a messed up matrix for sure.
Yeah, you get infinity for your force, which I think is probably a little higher than what you actually have in real life. Instead of measuring just the local A over F, we'll end up measuring many A over Fs, cross FRFs here. And the idea is, let's say at A1, F1, that the FRF does this, goes to 0, etc. I'll change my pen color to make this more exciting here. Another FRF that we're going to use in this calculation would be something more like this, where it has a peak where this FRF goes to 0. And what will happen is if we take all the FRFs at once and do the inversion times the operational accelerations, we hope that it doesn't go to 0 and that we can get a good, reliable estimate of forces. And you can see here, these orange dots represent where we want to calculate the forces. You mentioned a second ago, Steph, that we had some extra measurements. Well, those are some extra FRFs to other locations on the structure. In this case, the extra locations are scattered around. In this case, they're kind of bunched together. That's to allow us to do the matrix inversion. Which arrangement of FRFs, though, do you think would give better estimates for the forces?
Probably the one that's more scattered.
Yeah, because there's a better chance of different resonant frequency here at each of these different locations, right? Than here where they're all grouped together. They'd probably all have the same anti-resonance. Yeah, you have to pick those carefully. In that same data set, we can actually also do matrix inversion because we had those extra FRFs. And so what I'm going to do here is I'll create a new section. Oh, I need to stop editing my stuff here. I'll create a new section called matrix method, for example. Okay, and I'll go back here to my TPA model definition. I'll clear it. Now we're going to actually do matrix method. Let me also delete these, read the input basket. So Steph, what's our target location?
A microphone?
Yeah. So the microphone location and our paths are still the same paths, but now we're going to do matrix inversion where we've measured local FRFs here, but also at other locations. We can actually take these and use these as indicators, okay? We got our loads, half order, 1.5 order, third order. We're not going to use this mount table though anymore. Now we got all the FRFs and we got just a ton more FRFs all measured cross, etc. We got a ton more operational accelerations at all these additional locations. So we've really made the measurements go up quite a bit with this matrix inversion. And then which method would we pick here in TPA loads?
Matrix inversion.
Yeah, it's time for matrix inversion. Notice it's green and we can say, hey, let's create a full matrix inversion. Goes out and calculates it. This condition number you want as low as possible, at least under 1,000. It tries to tell you if there's one of those singularities where you have an inversion problem calculating the forces, but it shows you all the forces and everything else here. If you found that there's some very high peaks still, you might have to take some additional FRF measurements, additional operating measurements. And now we can look at the TPA results just like before, and it'll show us, if I update this, body 1Z is still the problem, but we calculated the forces a bit differently. Now we calculated them using matrix inversion rather than mount inversion, but we still got the same conclusions. The only insight I think that you don't get with the mount method is here we could see if the active versus the passive side, if the active side was a lot bigger, so we knew the mount was doing a good job. Now we see a bunch of FRFs there because those are the FRFs used in doing the calculation. And we can't do things like change the mount rate. So you don't know anything about the mount. And in the case of a stiff connection that you would be using the matrix inversion for, there really is no mount you can adjust. That is the matrix inversion method. Hopefully that all made sense. And I want to thank everyone for attending today. Hope it was helpful.
Thank you, everyone.